Record. All right. So guys, let's go ahead and get started. So, let me think. What's going on now? Let's do a little bit of review. Number of valence electrons. What's this guy? One.
3, 4.
4. So, what about ion? What charge is that ion? Okay, think about it for a second. 1 minus. That's the first one. Yeah, you do. That's on your way to your second class. Hold off. And like, if I'll let you out a little early so you can go take care of that.
It's not
Do what?
It's not the same thing as my next class.
That's what I mean. I'm gonna let you out a little early. Once so you can go and do that. Right. All right. Let's keep going, guys. So, we talked about properties. So, if everything is in the same group, then it means that they all have the same properties, right? The same kind of reactions are going to be happening. They react in a similar manner, etc., etc., etc. Okay. So talking about some of those properties, what is electronegativity? Who has a good definition? All right. Not atoms pull each other, but you're right about pulling. Pulling electrons, right? They, how strongly does an atom pull electrons around it? Okay. So what? Remember there was a trend. What was the trend? Top right. Yeah, these guys are all electronegative. These guys, not so much. Right? Electropositive. No. I'm going to say that. That's what we're going to get into a little bit today. There's a difference. I'm saying pulling, not so much of the pushing. Pushing doesn't exist. So, there's that. And then, why? Why is it that these guys are electronegative?
Do they have more protons?
More protons. So, as I move this way across the periodic table, you get more protons. More protons means bigger magnet. Bigger magnet means stronger pull. There you go. That makes sense?
Yes.
Okay, good. What about this way?
Less energy levels.
Oh, yeah. Less or more energy levels, right? Change your number of energy levels. What does that mean about those valence electrons? Farther apart.
Yeah.
Your distance between the magnet, your charges. Increase that distance, less of a pull, right? All right. So there's that. We talked about radius. What's the trend on the radius? How big the atoms are. Where's the small ones?
Small ones are in that place we were just talking about.
That way, right? Where are the big ones?
At the bottom. That far.
Over here. So, why? So, let's talk about up and down first. Why is it that we get bigger as we go down? More energy levels. Obviously, you're getting further apart, bigger. What about, why is it that we get bigger going this way? Not being pulled as hard because smaller nucleus, less protons, not as strong as battery. So, I just went over this with my AP today. We went over free response answers in AP today. Basically just reading each other's free responses and critiquing them, right? Kind of like in English. I'm sure you guys do that in English a bit. Same idea, except we don't care about grammar, we care about concepts. So whenever you say something like, they're not being pulled as far, a critique on that would be, yeah, but why? You know what I mean? You're a step towards the answer, but you gotta keep going a little bit more. Okay. So, there's that. All right. All good? Cool. So let's continue on with our talk about these periodic trends. Is that when you alive there?
Yeah.
All right. Just checking to make sure I didn't lose you.
Not yet.
All right. You need a shot of adrenaline or something? You got coffee? I got coffee back there.
I don't drink coffee. At least I never have.
Sacrilege.
No, it helps.
All right. So, today we're going to be talking about something called ionization energy. Okay? Ionization energy. Now, ionization. What do you think that means? How much energy it takes to make something an ion. Specifically, how much energy does it take to make it a positive ion? So, what do you do to make an atom a positive ion? Take away an electron. So we are stealing an electron from it. Okay? We're swiping it, absconding with it. Okay? So, we're going through and we're swiping an electron. Now, let me ask you this. How hard would it be to steal a test tube from this room?
Not hard.
Not hard at all. Right? Pretty freaking, yeah, or it did. I wouldn't be surprised. So, that's the thing, right? In this room, the amount, think about this as like a heist, right? If you were like Ocean's 11 heisting this room for a test tube, what type of planning would you have to do? None.
Well, I mean, if you're taking this one.
That's not a test tube, that's a udiometer.
How is a udiometer used?
Measuring the volume of the gas. But, yeah. So, we'll talk about that maybe if we get to ideal gas laws in this class
Just go back
later on. Anyway, so don't worry about that right now. That's not for you right now. What is about you is trying to plan a heist. So we're planning a heist now, and instead of a test tube out of this room, we want to steal all the money at the Bellagio Hotel and Casino.
That's hard.
Pretty hard, right? At that point, you need about 10 to 12 other guys and a full 2-hour movie. So, lots of explosions, right? Fake prosthetic noses, the whole 9 yards. So, a lot of energy is going to be going into that, right? So, what were those 2 things I told you always need to remember? First one, how big your magnet is. The distance, how far away it is. Okay. Same idea here. Okay. What is going to be an easy heist to pull off? Small magnet. Well, a test tube, yes, but in the atomic world, small magnet and really far away. Okay. Hard heists are going to be big magnets really close together. Okay. That's going to be your thing. Okay. So let's go through and give us some examples. Okay. Shoot. I wish I just had like a blank screen. One sec. Let me make a blank screen. Drive, new, slide, present, blank screen. All right. Where did my thing go? They're all up there. Good. All right. So let's say I go through and I have a sodium atom. There's my nucleus. There's my energy levels. My 1s2. My second energy level, 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6, 7, 8. And then I have one more electron at the end, right? Now, compared to how big this magnet is in the middle, how hard is it going to be to steal this electron? Not very hard, right? So, the way I like to describe it is, the sodium atom here, you know how like if you have a bike and you want to get a new bike, but your parents are like, hey, you got a bike, but it's old, it doesn't quite work as well. So what do? You can't, Yeah, you can't necessarily, you know, just get rid of it, but what you can do, leave it on your front lawn, unlocked, just kind of by the curb. Just be like, there you go. I'm gonna take away, I'm gonna turn around now. You know. So, that's kind of what sodium's doing here, okay? It's not pushing away anything. There's no active pushing going on. It's just stepping back, okay? Letting what happened happen. But yeah, it's the magnet here is like for the third period, the third row. How big is sodium's magnet? It's the smallest, right? As small as number of protons as you can get in the third row. And this is the same distance, it's still the third energy level. So, small magnet, distance, not a whole lot of force there. That's why you can go through and swipe up that electron pretty easily. All good so far? Cool. Now, same idea, but now we're going to be doing magnesium. Magnesium has 2 electrons in its valence shell and another proton in here. Well, we got a bigger battery, or bigger magnet, but the distances are still the same, right? So what does that mean about the strength of that attraction? It's a lot stronger, or a little bit stronger. Okay? So it means, is this going to be harder or easier to pull off this heist? A little bit harder to pull off this heist, right? So if we're talking about trends, let me head back to periodic table. If we're talking about trends, as I move this way, I'm increasing my battery, every time. I'm increasing my magnet, keeping the same distance, so it means the ionization energy, your Heist energy, is going to be going up, right? So, as I'm moving this way, ionization energy goes up. Okay. What about this way? Up and down. Think it's going to go up? So, small down here, high up here. How much energy is it going to take to, let's kind of draw out a thing real quick. 1, 2, 3, 4. If I have this electron and nucleus, how hard is it going to be to steal this guy? Let's say this is, you know, like medium, right? Then up here, how hard is it going to be to steal this guy now? It's going to be a lot easier, right? So, as I go down, the ionization energy is going to go down. As we go up, those valence electrons are going to be closer, which means ionization energy goes up. All good there? Same reason as electronegativity, right? It's still, I mean, you may have noticed the pattern, right? If I'm going up and down, what's the reason? Energy levels. We're adding and subtracting energy levels, right? If I'm moving this way, what's the reason? Protons. Protons. Protons because, yeah, basically how big is your magnet in the middle? Okay? So, same thing, but they just cause different effects. All right. So what do you think the general trend is? Going this way, right? So, these guys, high ionization energy. These guys, low ionization energy. So far, so good? Yeah. Okay. Now, here's the thing. Oh, okay, let's just check to make sure we're right. Hooray! We're right. Yay. Okay. So here's the thing. This is how much energy it takes to steal one electron. Now, if we go back to the other thing, the pop and pop. Now we're talking about magnesium. We go through and we steal one electron, okay? And I think it's around like 600. Anyone have their laptop out with p-table? Yeah? What's the, go click to ionization energy. Let's find this out real quick. Go to properties. And then click on ionization energy. Click on, what was that? 737. All right, so the first ionization energy there to get one electron was 737, I think it was kilojoules, but don't worry about that. It's a unit of energy, okay? 700 something, okay? How much is this one gonna be? How much energy do you think it's going to take to steal this electron now? The second electron. Look at this scenario. Well, what happens, how many protons are in the center for magnesium? 12. How many electrons do you have right now? 11. How big is that magnet compared to the electrons? A lot bigger, right? So, the second time I jump in and try and steal an electron, what's the energy going to be? A little bit higher, right? In fact, you go ahead and on the thing, hit, so right there on the first, click on it and go to second. What is it now? 1,160. So it definitely shot up. 1,660? 1,160. Okay, so it went up a little bit, right? Yeah. Sure. Yeah. It's kilojoules. It's actually kilojoules per mole. Don't worry about it right now. I'm looking for trends, not specific units and things. So, all right, so now we've gone through and absconded with this electron, okay? We're not done yet, though. I want a third electron out of this boy, okay? The third ionization energy, now obviously, you can imagine, it's going to be higher, right? But think about this now. Now, not only did I lose an electron, like I did with the second, also, how close are these guys? A lot closer, right? So these are a lot closer now. So you're not just going to have a little bump up. In fact, hit what's the third?
It's 2,285.
2,000, what was it?
285.
285. A big jump up, right? A big jump right there. Make sense? Because now it's a lot closer. So I'm going to right here and just do magnesium. I'm going to reset this for sodium. So first, second, third. All right. So now do the same thing, but switch over to sodium. So what's the first ionization energy for sodium? 495. All right, well, I mean, this kind of makes sense, right? We kind of predicted this would happen, right? We predicted that if we're moving this way, what happens to ionization energy? It gets smaller, it's less, right? And we see that, yeah? First ionization energy is less. Okay, so we've gone through, we've stolen one electron. So what's the second?
It's 4,562.
4,560 something?
62.
62. A little bit of a jump, right?
Well,
Why is it now jumping between first and second and not second and third? Because for sodium, the first one it took away, the second one it takes away now is on that lower energy level, right? You see how that works? No? So, as soon as you go from an outer energy level and you've stolen all those electrons, and now you're at an inner, then all of a sudden how much energy it takes to steal goes up a lot. Because now they're a lot closer together. Yes?
How hard would it be to steal an electron from hydrogen?
Not hard. In fact, hydrogen, how can I put this? A lot of times, hydrogen doesn't have its electron. A lot of the time. Yeah. So what is it really? What if hydrogen doesn't have an electron? What's left? A proton. Yeah, just one proton. A proton floating around. So we call it H+. You'll see it quite often. H+. You'll see that a lot. Especially when we get into acids and bases. This is basically why acids are acids.
How is it like dark blue then when you're here too?
Why is it dark blue?
Yeah, on the periodic table when it shows like the trace, you know?
Oh yeah. For what, ionization energy?
Yeah.
Helium, like on the ionization and everything, why was helium like the darkest one?
Because, think about it. With helium, how many protons does it have? 2. 2 protons, and its electrons are super, super close in that 1s, right? So, comparatively big magnet and super close, which means it's going to be.
So what would the same be for hydrogen?
So what?
So why wouldn't the same be for hydrogen? It's also one energy.
Right, but how many protons does it have? 1. Half the number. It's half as strong as this guy. There's also a lot of other reasons why hydrogen does it still. We'll get to it when we do acids and bases. All right. To get back on topic though. So, here's the thing. If we see a jump in ionization energy between the first and second electron, like that, you can tell something, right? What do you think lithium is going to do? Where is its jump going to be? Between which ionization energies? First and second, right? Just like sodium. Because you steal one of its valence and now you drop down to a different energy level. And that's going to be a lot harder, right? What about calcium? Why do you always do this to me? Calcium, when is it going to jump? It's going to second and third, right? What about boron? Third and fourth, yeah. Right? So it's going to steal 3 electrons pretty easily, but that fourth one is now at a new energy level. Make sense? We all good? Yeah.
Why does magnesium only jump by like 3 times, but then sodium jumps by almost 10?
So,
Even though.
one sec. Let me head back to the periodic table. I mean, a lot of times, whenever we're talking about things like that, it's,
Just because.
no, I don't want to say just because it's never just because. There's a reason. But the problem is that for me to explain the reason, you would need a fair bit more schooling.
Oh.
You know what I mean?
Yeah.
So, that's the thing, is like right now, like whenever you're a child, we learn that water's wet,
Yeah.
right? And then later on, now it's a big thing. Is water wet? Have I told you guys the thing about why water is wet?
Yeah. You told me about it.
Okay, water is definitely wet. Why? Okay, so you guys remember that, no, we've done this. Yeah, copper sulfate.
No.
Yeah, copper sulfate. Copper sulfate is an ionic bond. No, we haven't done this, have we? And then water is in the center. Have we done this? Yeah.
No? Well, yes, you explained that, but you didn't explain why
is this water surrounded by any other water? So it's dry,
Oh. What did I walk in
But I
on?
thought water was.
right? This water is not touching any other water, therefore dry.
The fact of the matter is, does the argument really matter?
Oh, you want to use like a semantic argument?
Oh,
Alright. But anyway,
Okay.
so to go back to this, right? Okay. We can kind of go through and look at this. So for, like, what, magnesium, right? As we go down this way, look at beryllium. It's 899, 737, 589. It's getting less and less as we go down. Makes sense. They're further and further apart. Okay? All good. Now, why is it that you said from, let's take a look at the second energy level of these guys. So here, it's up quite a bit, right? These are the lowest ones now, right? But look at how much these guys have changed. For beryllium, it's 1700, 1400, 1100, 1000, 1000. Okay. Now, if we go to the third energy level, right? Third energy level now, this is 7,632. So it did jump up a fair bit, right? So, what was it? It went from like 1,000 to 7,000. That's a big jump.
Yeah.
So, there you go. Okay. All right. Everyone get how you feeling about this? It's kind of like a trend, but there's that. Here's the type of problem that I continually see on exams. You'll see this all the time. So let me kind of go through and do this. So it's going to be like they'll give you a table, okay? And then they'll say like, here's the first ionization energy, the second ionization energy, third ionization energy. And they'll say, this is element X, Y, and Z. Now, you don't know what these guys are. The X, Y, Z is like a variable, right? Okay? And they're going to say, they're going to give you some of these ionization energies. Like, so let's say this is 400, 4,000, 6,000. This is 200, 500, 7,000, right? And then 100, 300, or 6,000. Something like that, right? Based on what you see here, you can tell me some information. So, which one of these guys is in group 1? X. Why is X in group 1? The first one is the jumping one, right? Between 1 and 2. What group is Y going to be in? 200, 500, 7,000. Group 2. Because this is your big jump, right? What about this Z? Group 2, right? Now, both X and Z are in group 2. Which one's higher up? So, out of X and Z, or I'm sorry, Y, out of Y and Z, they're both in the second group, right? Which one is higher up on the periodic table? Why? Why?
Because
It's higher.
Has higher numbers because they're closer together. Their valences are closer. Okay? See what I mean? Okay. So, stuff like this, like I can almost guarantee that you'll see a problem like this. If not in this class, definitely in AP. Because it's a type of problem. It's like, in math, you know how there's like a certain type of problem that you always see? questions, comments, concerns? All right.
When you say
say-
group, you mean like the.
Group, yeah. So these guys are groups.
Okay, yeah, that's what I thought.
Okay. You also will probably hear me say period, and by period I mean rows. Right? So kind of think of it like the first time it starts over. Like that's a period, right? It periodically starts over. So the first period is the top row, and then it starts over with S, right? And then the second row, second period, and then it starts over at 3. Then it goes and it starts over. So that's what I mean by if you hear me say period, I mean row. And if I say group, the column. Okay. So second verse, same as the first. Last time I asked you to get together and write a paragraph. This time, same thing. This time, explain ionization energy. Yeah. You can use just about anything short of interpretive dance. I know, right? I'm so constricting through dance.
Who wants to just,
Dance. I've interpreted dance. Like an you know, like interpretive dance, where it's like you dance based on how you everything. So look up interpretive dance.
I thought you meant like pop, and I was like,
No.
you can go there and dance.
It's a interpretive dance, like you like creative ways to express I disagree.
You lost it there.
Is there a tennis spot for this?
Yes, it's called ionization energy notes. Yeah. Yeah. Here's the thing. Like, it's hard. But this is the thing. How do I put this in a word tension? That's why I have to do it. That's why I have to
What is it called?
I mean, I do, especially if you guys are mine, if you guys have tried mine on me, I get back to you. This is easy. Yeah, this is hard.
Do I have ionization?
Kind of. It's how much energy it takes to shield. So, opposite would be like pushing. That's not pushing. That's not known as that. You know, yeah, exactly. So it's not quite like
What is this?
so I tell, like for oxygen, you want to get them like that. So A, valence. So how many are you going to want to bring in? Right, gain 2.
What band are you in last year?
So you're in gain 2. And then how many electrons are going to be? Are you going to have? You'll notice something. Is because for ionization, yeah, if you're going to the right, the first ionization energy, go to the right, you're getting more. Like it's harder to steal electrons the more to the right you go. Okay. SR? Strong.
Maybe it was a different one. I got one.
Don't check. I didn't think I gave you one before.
Okay, I'll go with it.
Yeah, you might have thought it was like SE or something.
Yeah.
Okay.
Because I messed up on time how many electrons they have.
Your chat.
Yeah, so when it comes okay, so this one, do you understand the ion line? Okay. So this one is just a complicated way of asking a very how many electrons are there? How many electrons are
Your
required?
hair did hide the knockout.
I thought it said all.
How many are in the world? Like I said, complicated way of asking.
What were you
Here is you're talking about things called base electrons. That just means the same number of electrons. So, for this one, for example, how many electrons is helium?
I've been told many times I look like Mr. Davis.
Helium?
That's one of the worst things you can do.
Hydrogen minus that
You know, my friends used to call me and they saw my dad. And they're like, no, you don't look like Davis.
lithium plus has no lithium.
Is it
Oh,
Yeah, that's two. Yeah, it's lithium plus. So that always tricks people up because you add electrons, so it's a negative. But yeah, see, all of these have two electrons in them, but they're different. Okay? So that's what isoelectron is. So which one of the B or C, which one is an isoelectron?
Plus, I really
If
don't.
you look at your C, it's just saying yes or no, B or C. And then for these, you just find how many electrons, and then Yep. Okay. Do you need help? Have you managed through the group? Ran through the group? Because that's the whole point of this. I want you guys to teach each other.
I didn't write a whole lot. You're gonna be looking so good though. He'll be wanting to.
Higher iron. Y'all good?
The energy level.
We get off
What's
TikTok.
ionization level?
I don't care. We get off social media. You seem to be having a day, and I understand.
Could be small.
But still, I'm gonna say this. I am real tired of people using their phones for things that I don't have to give attention in the classroom. So, with that in mind, if you're done with everything in this class, you're an AP student. I guarantee you have other work to do. So, I'm gonna say that. If you are completely done with everything, so I don't mind if we have 2 or 3 minutes left. We got plenty of time left.
Do I take a picture of this?
We're done. We're done with this.
This is what it was, right?
Little more kids. So there's 2 reasons, right? What are the 2 reasons? Why is it that when you go this way, what's the reason? And when you go this way,
48.
what's the reason? Well, you got the up down, and then the left right. Why is it that the further you go to the right, electrons, so bigger magnet. Yeah, one sec. I'm on the third ionization energy. Let me switch to first. There you go. Is that better? Yeah. So, what do you mean? Oh, right here? Or are you talking about right here? Right here? Yeah. As you move down, it's getting less and less and less. Yeah. Actually, if you want to open up on your phone book, go ahead and look at it. You can see the numbers as well. That way you can kind of see. And sometimes those colors are, yeah, a little misleading. I mean, if it's, going from 1,000, or 1,200 to 1,100, the colors aren't going to be that. But you can still see it's going down. If you're going left and right, you're changing the size of the magnet because your valence shell, the outer shell is okay. Alright, it seems like you guys are about done with that. So I have one more trend to talk to you about. Okay? And it's less of a trend. It's a trend. So, up here in this corner, you see this little green block? That light green block? Those guys are non-metals. Not metals. Non-metals. Okay? We all good there? Non-metals. Okay? These guys, including that, are metals. Everything over here is a metal. Okay? So these things, the kind of teal right in there, are metalloids. Metalloids, which means they're kind of like a metal, they're kind of not a metal, a little bit in between. Metalloid. Chemists are the best neighbors, man. So, here's the thing. That means that you can kind of see, right? Not metal, kind of metal, metals. So what do you think is more metallic? Potassium or iron? What's more metallic? Potassium is more metallic than iron. Here's the thing. How many people have seen pure potassium before? Bananas have potassium in it. But usually it's like, huh? Yeah, there's lots of things that have more. Like everyone's like, oh yeah, drink orange juice for vitamin C. Milk has more.
Oh, I love milk.
Alright guys, we're getting off topic. Bring it in. So, here's the thing. When I'm talking about a metal, bring it in. When I'm talking about a metal, I'm talking about something that is a solid. Well, think about like pure carbon. Okay? What is pure carbon? What's an example of pure carbon? Charcoal. Charcoal is pure carbon. Right? Diamonds are pure carbon. Graphite is pure carbon. The stuff in your lead, pencil lead, that's pure carbon. Okay? Kind of hard, right?
Sure.
Can you break a diamond?
Not without another diamond.
Yeah. So here's the thing. There's certain things. Metals are known for being what's called malleable. Malleable. You can bend them. If I took a piece of wire, metal wire, and I bent it, but it snapped, would it be very metallic? No. You want something malleable. So, iron is less malleable than potassium, which means it's less metallic. I know, right?
That's it.
Usually you think metal is like super hard. Yeah. Alright. Usually you think of metal as being like really super hard. It's not. Okay? So, francium. Francium was the biggest one of them all, right?
Yes.
It's also the most metallic.
I was thinking.
There is a metal band called francium because they're the biggest, most metal band out there. They're complete nerds, man. I love them. Now they're you know, they definitely do rock. All right. So that being said, everyone got that trend. That trend's pretty simple. You can't. I don't really have an explanation for it right now because we haven't gotten into different types of bonds. All right. Homework. On your way out. Big one. Pass it around. So guys, this is actually, it's not that bad. For example, number one. Let me grab one. I need to grab one. Alright, so number one on here, for example, says rank the following by increasing atomic radius. Alright, so the following by increasing atomic, so carbon, oxygen, aluminum, and potassium. Which one's the biggest? Which one? Oh, no, I'm sorry. By increasing. So which one's the smallest? Oxygen smallest. Which one's the next? Then carbon. Then aluminum. Then? That's answer number one. That's it. More or less. Some of them maybe a bit trickier. Maybe. But yeah, that's basically it. When are all things due? Don't you love that rule?